Hello. Is everyone hopefully not succumbing to the food coma yet and ready to come back for our last after lunch session? Great. Well, my name is Irene Henninger, and I'm an avalanche forecaster with NWAC, where I primarily forecast for the West Central and West North zones. It's really exciting to be here with you all today, finally celebrating an in-person NSAW for the first time in a while. Before we jump into this last session, we're going to hear from Kevin Groove about an exciting program that will be coming to the Pacific Northwest this fall.
Okay, thanks, and thanks to everyone at NWAC for putting this event on. ISSW has been mentioned a couple times today. How many of you know what ISSW is? How many of you have a deep understanding of what ISSW is all about? A few of you, so that's what I'm here today, is to share a little bit about what ISSW is, the International Snow Science Workshop. It's an interdisciplinary exchange of ideas and experiences among the snow science, avalanche recreational or the research and practitioner communities. It's a week-long conference that happens every 2 years, and it rotates between the US and Canada and Europe. The last ISSW in North America was 2016. We are super excited to host ISSW in Bend, Oregon a year from now. So October 8th through the 13th, ISSW will be in Bend. A little bit of historical perspective. The conference started way back in the 50s and 60s with some informal meetings amongst the community. In 1971, Ed LaChapelle actually hosted a meeting in Seattle with this idea of exchanging ideas amongst the Avalanche community. 1982, my alma mater, Bozeman, Montana State University, held the first meeting where they termed the coin the International Snow Science Workshop. And they also created the theme of the conference, which happens to be a merging of theory and practice. So that's the whole idea of the conference. We're super excited to be hosting this in Bend a year from now. It's a week-long conference. It starts on Sunday evening with host reception. There are presentations. There are poster sessions. There will be panel discussions, evening functions. There will be a lot of coffee and beer absorbed. So if you are interested in coming, you don't have to be a professional in the community. Many of the folks that come will be. Some of the key deadlines here, those of you in the community that will be submitting abstracts, they will be opening in January, closing in April. We encourage folks from the research community, from the practitioner community to submit abstracts. And then if you're planning on attending the conference, you can attend for the entire week. You can attend for one day if you just want to get a taste of what ISSW is all about. Those dates and deadlines for registration, March 1 will be early registration, which will be cheaper, and then the registration, regular registration in July. So that's ISSW. Evening events will be happening every night. And we just really look forward to getting the entire snow science, avalanche research and practitioner community together in Bend to hug it out. So what questions do you have for me? I think I might have a minute or two for questions about ISSW.
Can you give some titles just to see what kind of topics that you talk about at this conference?
Yeah, so we're working now we have a science team that's working on 12 themes. And so everything from avalanche education will be a theme. We're currently working on a theme that will be titled something along the lines of, so certainly all the science around crack propagation and all the science around the snow component, but the psychology component. We're talking about having a theme focused on worker health. That was brought up, Dallas brought that up in the AAA, where there's a lot of focus and energy right now around mental health from the people out on rescues and that kind of thing. So that gives you a general sense. On our website, issw2023.com, soon we will have all the themes posted, so you'll get a chance to take a look at everything that will happen at the conference. Other questions?
Are you guys looking for volunteers, or is COAC going to do volunteer?
So this is not a COAC event, but we are looking for volunteers, and we'll have a volunteer structure so that if you do want to volunteer, you'll be able to put in a certain number of hours and then get registration for a certain number of days. There will be a nifty equation. But yes, we will be needing and seeking out volunteers, so keep tabs on the website. There will be a link to volunteers. I'm currently also tapping lots of people on the shoulder for volunteering and for helping out. It's a big project. I just hit up Mark Moore this morning for a potential poem for the opening ceremonies. I don't know whether or not that's going to happen, but I thought that could be a really cool touch to the Pacific Northwest. Mark and Rich Marriott co-chaired ISSW in Sun River, Oregon, of all places, just south of Bend in 98. Is that what you said? 1998 was hosted in Sun River. So don't be surprised if you get tapped on the shoulder, Dallas and other folks, to submit an abstract or NWAC folks are already helping out with various things.
Are you arranging any room block or room rate for attendees?
Where'd that question come from? Tell me again the question.
Are you arranging any hotel room blocks or room rate?
There are room blocks. The conference is at a place called the River House in Central Bend, and there will be hotel rates through the River House. So you can stay right where the conference is. There's also lots of places to stay in Bend. Yes. Thank you, appreciate it.
Very much looking forward to Mark's poetry introduction to the ISSW, in addition to having a long-awaited ISSW after quite a long hiatus. Great. So, our last session for today revolves around our mountain snowpack, how we can monitor it and understand it, how it's changing, and what type of snowpack we may see this winter. Our first guest here is Dr. Alia Khan. She's from Western Washington University, where she leads the Western Washington Cryosphere Studies and Aquatic Biogeochemistry Lab. Dr. Khan and her students study factors that affect snow and ice melt. Over the years, Dr. Khan has traveled the globe performing research on snow, sea ice, glaciers, and ice sheets. When not in the mountains for work, you can find her out on her splitboard or introducing her daughter to the glorious snowpack of Western Washington. Welcome, Dr. Khan.
It's such a pleasure to be here. Thank you so much for inviting me to speak today. Let's see. Okay, here we go. So I'm going to be talking to you guys about my area of research and what I think is a large driver in our changing mountain snowpacks, which are light-absorbing particles and snow algae. So I'll describe these more. Just as Irene mentioned, I'm an assistant professor in the Department of Environmental Sciences at Western Washington University. I have a research group. If you're interested in a master's degree or know of somebody, send them my way. I'm always looking for motivated students to join our group. And I also teach lecture and lab field courses that explore our local snowpack and watersheds. So today I'll start with some background on snow albedo. This is probably a refresher for a lot of people, but important to our larger questions of the role of light-absorbing particles and their influence on radiative forcing of the snowpack, and then also describe some of the research that we're doing here in the Pacific Northwest. So just to step back first before we dive into snow albedo, the Earth's energy budget is very important. And so the Earth's energy budget is the balance between the amount of energy that reaches Earth from the sun, and that's my daughter in the background, and the amount of energy that flows from Earth back to space. So here, the yellow is all the incoming solar radiation, the red is the total emitted back from Earth, and what we're really interested in is what's going on at the surface of the Earth. So why does seasonal snow matter to the global climate and to the Earth's energy budget? It is essentially, the cryosphere acts as a reflective shield, or it's Earth's mirror, so it's reflecting back a lot of the incoming, almost entirely all of the incoming solar radiation. Fresh, pristine, perfect powder is going to be reflecting about 90% of the incoming solar radiation. Whereas open water and bare ground, so as we start to lose our snow cover, we expose more bare ground. As we lose Arctic sea ice, we're exposing open ocean. This has a much lower albedo, and it absorbs more of that incoming solar radiation. So the presence or absence of snow and ice affects the heating and cooling over Earth's surface, and this influences the Earth's energy balance. So just a background on albedo. So this describes how reflective a surface is. It is the ratio of the reflected light to the incoming radiation. And it's unitless, and it ranges from 0 to 1. So a perfect absorber has an albedo of 0, and a perfect reflector has an albedo of 1. So snow and ice have a very high albedo, and they reflect about over 90% of incoming solar radiation. So here we're looking at the Arctic. This is the Arctic sea ice. This is part of why it's so important. As we lose the sea ice, we're exposing more open ocean, which absorbs more solar radiation. Here is a schematic derived from MODIS, the Moderate Resolution Imaging Spectroradiometer, which is on NASA's Terra satellite. So this is a passive sensor that measures radiation emitted by the sun and reflected back by Earth. So this is one of the science community's best tools for measuring snow albedo across the globe. And so you can see here, as we march through the lifetime of the MODIS satellite, so it was launched in the early 2000s and is still active right now. And so we have a pretty long satellite record of snow cover. And because it's a passive sensor up in the Arctic, we don't have any measurements over the polar winter when there's no light. All right, we're almost done here. But so we can start to look at trends in snow cover using our satellite record of snow albedo. So here, the snow cover refers to the amount of land covered by snow at any given time. When we look at the annual record, we might not see much of a trend right now in total snow cover. But when we start to dig into the climatology or looking at different seasons of the year, we can see that there's the largest decline in the spring and summer seasons. So between 1972 and 2013, the US snow cover season became shorter by nearly 2 weeks on average, and the largest change has taken place in the spring, shifting snow earlier by about 19 days since 1972. And so what I'm going to talk about is why I think one of the really interesting roles in looking at this decline in snow cover and snow albedo are light-absorbing particles and snow algae. So light-absorbing particles are comprised of several different things, including black carbon. So as everyone here is highly aware of, we have a lot more smoke generated by wildfires, and our increased land aridity is also, and increased temperatures are also exacerbating this wildfire season. So black carbon comes from the incomplete combustion of fossil fuels and biomass. Then we also have biological constituents like snow algae and dust such as from coal mining or naturally occurring dust, mineral dust. So here is, these are spectral albedo measurements that I've collected in the field over the years. And up at the top is a clean snow spectra, or essentially snow without any light-absorbing particles. And you can see on the y-axis is the albedo, so from 0 to 1. And the snow without any impurities has a very high albedo, closer to 1. Whereas as we look at these spectra of snow with algae and with dust, the albedo is lower. So on the x-axis is wavelength from 350 to 1300 nanometers. And the region that is most important for, or the region where the light-absorbing particles have the strongest influence on the albedo is in the visible wavelengths. And so you can see the algae spectra, the red and green lines, have these very clear absorption features, and those are the pigments of the algae. And then this black line down here it's absorbing very uniformly in the visible wavelengths, and so it has a very broad impact on the visible albedo. All right, so we'll start with black carbon. So it is a light-absorbing aerosol, and when it's freshly emitted from forest fires and fossil fuel combustion, it has a direct impact on atmospheric heating. So these particles are highly absorptive, and they lead to a direct heating of the atmosphere. But as they age and are suspended in the atmosphere, they become coated by secondary organic aerosols like sulfates, and this can lead to an indirect effect on the climate because they change from a very hydrophobic dark particle to a more hydrophilic, lighter colored particle, and they can serve as cloud and ice condensation nuclei. So in the atmosphere, there is some very complicated chemistry that can occur with these particles, but I think it's important to note that black carbon is the second most important climate warming agent after carbon dioxide, and the residence time is several weeks as opposed to several hundred years. So in terms of a climate standpoint, we could have a stronger impact on the climate. We could see near-term solutions by curbing black carbon emissions and having stricter policy on black carbon emissions. And so what we're interested in here today is what happens when these particles are deposited on the surface of the snowpack. And I just want to point out, this is a schematic from the NASA GEOS model, and here you can see how, so the green is black carbon, or black carbon from forest fires, and you can see up in the Pacific Northwest, throughout the annual cycle, you can start to see the wildfire season. Down here in the Amazon, there are lots of fire emissions, and there can be long-range transport. And I do a lot of work in the polar regions, and so we're also interested in this long-range atmospheric transport of black carbon. I think everyone here is very aware of the impact that our hotter summers and just longer wildfire seasons are having on the smoke and the air quality. And this has a large impact on especially the snow on glaciers that are around throughout the summer. So how many people like to ski on glaciers in the summer? Right, so awesome, lots of people, yeah. So this, I think, especially the black carbon, we're gonna see a stronger impact on the glaciers and the summer snowpack for spring and summer skiing. All right, so we know that black carbon the warming caused by black carbon is concentrated in the northern hemisphere. This is very likely, and we know that we're pretty sure this leads to earlier springtime melt and a reduction in snow cover, but this magnitude is still highly uncertain. Thanks. Okay, and so the radiative forcing attributable to black carbon deposition in the cryosphere is reported with 90% uncertainty bounds. It's also not possible to detect black carbon in snow with remote sensing. I'm going to speed up because I just saw my 5-minute warning. And so as a result, we need more ground observations of black carbon in the cryosphere. And I'll just note, this is what a lot of the work that my research group is doing, and a lot of my previous work was trying to develop a larger ground observation record of black carbon in snow across the cryosphere. We can also use aerosol reanalysis models, global aerosol transport models, to track wildfires and the smoke deposition. So for example, here you can see a wildfire in the Canadian Arctic. This was a study where we were looking at impacts on the Greenland ice sheet, and so you can see the smoke transport, and so we're doing some of this work here in the Pacific Northwest as well. I'm gonna just kind of speed up here. So the main the takeaway here is that there are a lot of complex feedback processes occurring. So we have black carbon emissions, the deposition on the snowpack. This reduces the albedo, leads to an increase in snowpack temperature. But through each of these steps are a variety of feedback processes. And so each of these feedback steps could be its own PhD thesis of trying to understand these mechanisms. I've been a part of some work where we were looking at the impacts of black carbon on snowmelt in the Andes. And essentially we found that Closer to Santiago, there was an impact on snowpack shrinking by up to 241 millimeters of water equivalent. And then it was much less down in Patagonia, where the concentrations are lower. Similarly, we've looked at impacts of the black carbon footprint of human presence in Antarctica. So again, we can look at the deposition of black carbon, what this means for increased energy absorption at the surface, and how that then translates to snowmelt. All right, so dust on snow, this is an example from Tom Painter's group in southwestern Colorado, where dust from Utah will often blow into the San Juan Mountains. And you can see that on this hydrograph up here, from January to December is on the x-axis, discharge on the y. And after the dust loading event, the peak snowmelt was shifted forward about 3 weeks. So these dust deposition events can lead to lower albedo and quicker snowmelt. We have dust here in the Pacific Northwest as well, and this is something we're also exploring in terms of those impacts. And then lastly, biological constituents like snow algae. Real quick, how many people have heard about this Living Snow project? Awesome, yeah, okay, so I'll talk a little bit about a collaboration that we have at the end. But so my group, we're looking at essentially the impacts of snow algae on snow albedo. And so the pigments and carotenoids in snow algae enhance solar radiation absorption. And again, similar to black carbon, this increases the energy absorption at the snow surface and enhances melt. This is some work from Antarctica. We're looking at red and green colored snow algae and the impact on snow reflectance. And it's a very similar approach to what we're taking here in the Pacific Northwest. So essentially, we can take the difference between the algae-free snow and the green and red colored snow algae and calculate the instantaneous radiative forcing that's attributable to the presence of these snow algae communities. And then we can take that and calculate a daily radiative forcing. And so from there, we can calculate how much snow is melted because of the presence of the snow algae. So here we're finding that about 3,700 million cubic meters of snow is melted annually due to the presence of snow algae. And so we're essentially taking the same approach here in the Pacific Northwest. So, so far, there's been relatively little attention given to how snowmelt is driven by some of these biologically active constituents. So one of my grad students, Shannon Healy, we have a paper in revision where we've been using a UAV to map the snow algae communities. So we can fly this multispectral camera, map where the snow algae are present, model the impact on the albedo, calculate the radiative forcing, and we're seeing that snow algae actually have an average instantaneous radiative forcing that's greater than the dust attributions to snowmelt in the Rocky Mountains. So again, a driver of snowmelt that is pretty interesting to explore. Then because of these specific pigment features, we're starting to scale up to using satellite imagery. And so here is a seasonal progression we're looking at Sentinel-2 and looking at how snow algae are growing throughout the spring and summer on, this is Mount Baker. So we're out in the field collecting snow samples to validate our satellite imagery as well. And then, as I mentioned before, we're using models to look at the smoke deposition fluxes as well, so interannually, and we're starting to dig into some of these more seasonal trends to see, for example, this year, I'm sure we'll see that there's a much stronger smoke signal into the fall, which is also important for our glacier mass balance. So based on the IPCC, we have a projection for increases in fire frequency into the end of the century and likely beyond. And by the 2040s, wildfires will increase by 51%, and the area burned will increase by 59%. Then we can also model dust and smoke deposition. We have some funding that's just ramping up, so stay tuned. We have lots of results coming. I also want to thank NWAC for helping us get a pyranometer set up at Pandome. I think Irene and Andy were instrumental in that. And so we'll use these local radiation measurements to then use that in our modeling of the radiative forcing of these parameters. I mentioned the Living Snow Project, and so also, how many people have collected a sample for a Living Snow Project? Awesome. Yeah, so part of what, so I'm collaborating with Robin Codner and others, and so my group, my students and I can use the locations where you guys have seen snow algae and use this to validate our satellite imagery. So in conclusion, deposition of smoke-derived black carbon and fossil fuel-derived black carbon are being altered due to a changing climate, and snow algae respond to liquid water availability, and climate change will likely impact their seasonal cycles. So together, these light-absorbing particles like black carbon and snow algae are impacting snow surface albedo in the Pacific Northwest. This increases the local radiative forcing, which leads to snowmelt. And so stay tuned. We've got a lot of exciting results coming online soon. If you see an opportunity to collaborate, please reach out to me, especially if you know of students that might be interested in getting involved. I'd love to talk to them. And with that, I'll thank funding sources and open it up for questions. Thank you.
That is absolutely fascinating research. Thank you so much for sharing, Alia. And now we can open up to questions. Have we got any questions? Oh, got one.
Heavy cloud cover might reflect. Does the smoke cover provide any reflection at all? Or is it all absorptive? Does the heavy smoke cover provide any reflection at all, like a heavy cloud cover might, or is it all absorptive?
That's an interesting question. So, yeah, I think it varies a lot depending on, like I mentioned, when the black carbon is freshly emitted, it's going to be highly absorptive and likely have a very direct impact on atmospheric heating. But if those smoke particles stay suspended in the atmosphere, that's where then they can become coated in secondary organic aerosols, which changes essentially the color of their coating and also their ability to form clouds and serve as ice condensation nuclei. So then there is an indirect effect on atmospheric cooling through that process.
Thanks.
Yeah.
Thank you. And we've got a question from Mark.
I was wondering if there are any studies or any research directed toward being able to alter the algae growth or the color of the algae from red to white or green to white so it doesn't reflect. I mean,
Interesting. I'm not familiar with any research like that. It's interesting. I didn't have a chance to go into too much detail, but the algae have an interesting life cycle. So, and there's still some questions about their life cycle, but the general working hypothesis is that they start out green and then form this photoprotective pigment, which is astaxanthin, and that gives it the red color. So they go through this life cycle. Yeah, I think it would be very challenging to try to alter their color, but maybe with bleach, but yeah, not that we want to do that.
You probably wouldn't want to do that. It's not really
No,
environmental.
that was a joke, total joke, yeah. Yeah.
Start genetically engineering the algae.
Right.
We have a question right back there.
I don't know if you covered this already or not, but does the smoke affect the algae growth? Like, would the smoke covering the algae affect the light the algae's getting and therefore decrease the amount of algae in the snowpack?
Totally. I mean, so that's a great question, and that's something we're trying to kind of dig into with separating out analysis for these three different primary biogeochemical drivers of snowmelt, because same with like atmospheric deposition of nutrients or things like that. So I think that's an interesting question that, yeah, we're still trying to answer. Great question. Thanks.
there was a lot of data there, but you may have said it, but I missed it. I got the impression from the graphs that algae is increasing. Is that due to heat, or is that not true? Like,
Well, so that's what we're trying to satellite imagery, because for essentially the first time we'll be able to look at a time series over the season and over multiple years. And so in general, there are some questions of, like, say in Antarctica, I'd say it is like the habitat for it to increase. There's a lot of potential habitat for them. In the Pacific Northwest, it might be a different story where we might reach some sort of critical threshold where their habitat is right, like as the snow melts quicker, there's just sort of less for them to grow on, and same with the glaciers. But they do respond to temperature and liquid water availability, so there are, as the snow melts, they will definitely proliferate. But then once the snow is gone, right, they kind of go back to the soil.
Looks like we have a question from the online audience.
Oh.
Indeed, we have a question from the online. There's some interest in what causes more snowmelt, algae or dust.
Yeah, so as I showed, can I click back? I'll go. Let's see if I can get back to that slide. Maybe it's further than I thought. Here we go. So this is a study that we have in revision right now, but our calculations for this particular site is that, so this is the Healy et al. 2022, my grad student Shannon, we're seeing that it's about on par with this previous report from southwestern Colorado. It's gonna definitely vary by location, right? Like by the concentration of dust, the proximity to dust sources, and similar to the algae, right? Like you guys have been out, you don't necessarily see the snow algae everywhere, but it's ephemeral and it covers different areas at different times. So I think this is a question that I'm really excited to explore more, is kind of what are the primary drivers? Is it dust? Is it black carbon? Is it algae? And my guess is it's each of those at a different point in time and perhaps at a different location as well. So location and time dependent is my guess.
One more question.
You mentioned there's a life cycle. Is that like a yearly seasonal thing we should be aware of? Like, is there a mating season? Should we stomp them out with our skis in the spring? Or?
I know, I think, yeah, that's an interesting question. So there's like from like a conservation biology perspective, people might say, let's protect the algae because they are very interesting ecologically. But yeah, we do see that they have an impact on albedo and melt. So I think we should just let them do their thing, and yeah, but yeah, good question. Yeah. Cool.
Wonderful. Thank you so much, Alia.
Thank you.
And so next up, we are going to be hearing about an amazing resource we have in sections of the Mountain West and learn about how we can get involved to help researchers as they seek to understand our changing snowpack. Nina Aragon is a PhD student in water resources engineering from Oregon State University. Her research focuses on combining modeling, remote sensing, and field observations to improve our understanding of the mountain snowpack and downstream water resources in the context of climate change. You're likely to find Nina out playing in the snow on her splitboard and merging her love for science, the backcountry, and her community with much of what she does. Welcome, Nina.
Thanks so much. Hello, everyone. Yes, so today we are going to be talking about mountainsnow.org. snowpack modeling and monitoring changes. Really quick, want to give a shout out to all of the people that I work with. So David Hill, Emilio Mayorga, Anthony Arendt, Gabriel Wolkin, Ryan Crumley, Katrine Wilkstrom-Jones, and Elizabeth Berkowski. We have a really awesome team that makes all of this possible. Okay, I'm going to start this presentation off today by talking about snow monitoring and how we can use the data that we have available to see trends in our snowpack. I'll then go into a brief overview of the Community Snow Observations CSO Citizen Science Project and discuss why these data are so important. We'll also take a look at how these observations improve our snow models, and finally we'll take a look at our real-time snow modeling application. All right, so as everyone here is probably familiar, snow is the best because we get to go out in the middle of winter and get deep patterns and face shots. The landscapes are beautiful, it's super fun. But seasonal snow also plays an amazing role in our hydrologic cycle. So some of this was just spoken about. I don't know why that changed. Some of this was just spoken about, but we also use, or one of the biggest services that Snowpack provides is that it serves as a natural reservoir that bridges winter water storage to summer water availability when both human and ecological demand are at their highest. Despite the importance of seasonal snow, though, the distribution of mountain snowpacks are fairly unexplored in many parts of the country. In order for us to understand how snow is distributed across our mountains and how our snowpacks are changing over time, we need to monitor our snowpacks. And monitoring snowpacks requires data. And there's three main types of snow data that I'm going to talk about today. So we can have in situ, on the ground data, we can also get remote sensing data, or we can get modeled snow data. We're gonna take a look at each type of these and see what kind of trends they can tell us about. So in situ or on the ground snow observations serve as a reference point for other types of snow data. Manual observations are typically less frequent in time than our automated snow observations, which tend to be at a really high temporal resolution. And we can measure all sorts of snow variables on the ground. We can measure depth, temperature, density, grain size, albedo, which we just spoke about, but we can also measure our snow water equivalent, which is something that I'll keep coming back to today. And the snow water equivalent, or SWE, is just the depth of water that you would get if you were to melt a given depth of snow. Okay, when I say manual snow observations, I mean humans out in the field measuring snow characteristics. The first organized snow monitoring efforts in the United States started back in the 1930s when Congress formed the Federal State Cooperative Snow Survey. This survey established regular monitoring sites called snow courses where people went out and did monthly manual measurements of snow variables like snow depth and SWE. The snow survey has provided one of the longest periods of record for any of our observational data sets in this country. We can use this really long period of record to identify long-term trends in snowpack. So one study, which this image here is from, analyzed snow course data and found that 90% of monitoring sites with over 60 years of records showed declines in our April 1st SWE, which is usually when we have our deepest snowpacks. But of course, we can also automate these on-the-ground observations, and in the late 1970s, automated snow monitoring networks were established in the western US. One example of this is the Snow Telemetry or SnowTel network, and a lot of you are probably familiar with this for looking and getting backcountry data before you go out into the field. These monitoring sites collect snow variables like depth and SWE, but they're also usually co-located with meteorological stations, and all of this data is collected at a really high temporal resolution. And though the automated snow station network has a much shorter period of record, we can still look at this network for trends. So in this image here, we're looking at stations with significant increases in SWE, and you can see that there are far fewer sites with significant increases, which are indicated in blue. I think there's only 3 of them, compared to SnowTel sites with significant decreases in SWE. And one of the things that's really unique about these sites is that you can combine the snow data with meteorological data that's available there to start to understand why we may be seeing these trends. So a study by Hu and Nolan looked at meteorological data and found that days with precipitation have significant increases in temperature compared to days that do not receive precipitation in the spring and winter at our snow-tell sites. This means that when precipitation's falling, we have warmer temperatures, but we need cold temperatures to get snow. So this is just useful in understanding some of that why behind the trends we're seeing. Okay, things got extra exciting for snow monitoring in the 1980s when we gained the ability to monitor snow via remote sensing. So for example, we can put sensors on planes like the ASO project, and we also have amazing satellite imagery that's out there. Remote sensing data gives us a really spatially more complete picture of our snowpacks, and that is fantastic to ask different types of science questions. Remote sensing data can help us answer questions about these spatially continuous variables. So for example, this figure here shows us trends in snow-covered area for mountainous regions. And this paper looked at 18 years of data in the MODIS satellite set and found that 78% of global mountain areas are increasing a decrease in snow-covered duration of up to 43 days and a decrease in snow-covered area of up to 13%. So this is a much shorter time period. There is more data available for this, for these MODIS data sets, but we can just answer different types of questions using this remote sensing data. And this brings us to our last type of snow data, which is snow modeling. Snow models provide additional data, and most of the snow models that exist out there actually incorporate in situ or remotely sensed data into the model physics in order to create snow estimates that are continuous across space and regular in time. And this is useful for all sorts of applications and analyses. For example, a 2021 study by Welty and Zhang used a modeled snow product from the University of Arizona in order to understand the characteristics and causes of extreme snowmelt. So this image that you're looking at here, I'm just gonna see if I can use my pointer. No, okay. Does this show up, the pointer on here? No, okay, that's okay. Anyways, this image shows the average 2-day melt for the 10 largest melt events across the entire United States. And one of the things that really stands out to me is note that here in the Cascades, some of the largest extreme snowmelt events are located here. And this study has also found that in the last 30 years, there's been an increase in frequency in these extreme snowmelt events, which has implications for all sorts of different hazards and management topics, though the magnitude of these extreme events hasn't changed significantly. Okay, so in most of these regional to national scale snow modeling efforts, observations from automated snow station networks, such as SNOTEL, are the primary source of data that gets assimilated into our snow models. From a mountain snow perspective, one shortcoming of these networks, not sure why these keep changing. One shortcoming of these networks is that they're typically located in really accessible locations that are not at risk of hazards such as avalanches. And because of this, many of our remote alpine mountain areas are actually missed when we're doing on-the-ground data collection. In this image here, we're looking at Snoqualmie Pass, and you can see that in the kind of bottom left of the domain, we have 3 of these SNOTEL sites, and all those blue dots are actually observations that were submitted by snow recreationalists or professionals. And so you can see that it really fills in the gaps in our observational record across space. It's also worth pointing out that the places that we need data are usually the places that are fun to ski. So keep that in mind when you're out there skiing. You're able to support these snow monitoring efforts this winter by contributing observations to the Community Snow Observations or CSO project. The Community Snow Observations project was launched in 2017 with the goal of developing a global network of citizen scientists who would collect and submit measurements of just snow depth. So really low barrier to entry. Anyone can participate, but we have prioritized participation by snow professionals and recreationalists. These users have been prioritized because you all are going to the places where we're missing observations. And participation is super easy. There's only 3 simple steps. You go out somewhere in the backcountry as a starter, and then you measure snow depth. This is typically done with an avalanche probe, since we all have those in our backcountry kit anyways, and conveniently they have measurement units on them. And then you can submit these observations via an app. So the SnowScope app is the app that automatically will send this data to us. Or you can use SnowPilot, which is a desktop platform that a lot of avalanche professionals use to submit observations. It's a really simple app to use. You just push the plus to start an observation. Then you select snowpack height. You record the snowpack height. And then once you've submitted that, you can view it in that list form or on a map. Right. So now we can talk about our snow model, which is named Snow Model. And Snow Model is a physically based, spatially distributed snow evolution modeling system. It models the change in the snowpack over the course of each winter. So the inputs to the model include weather information, elevation, land cover, and then it spits out really interesting variables like snow depth, SWE, snow density, snow melt, all sorts of things you might be interested in. And all of these variables are modeled so that they're continuous across space and regular in time across any spatial domain you select. So this animation that's playing shows the evolution of SWE across multiple seasons in our northern Washington domain. And while our snow model does a pretty good job of simulating snowpack evolution over the course of each winter, we can incorporate on-the-ground snow observations through a data assimilation process, and this helps us to improve our model. Data assimilation compares modeled SWE estimates to observed snow measurements, and this provides a correction factor for our model. In this figure, you can see that there's this dark blue line, and this is the baseline run for our snow model. This is what the model would guess our snowpack, how our snowpack evolves over the course of a winter if we added no observations and just forced it with that forcing data I just mentioned. We can then submit an observation. So that's what that red dot is. It's an observation that someone submitted, and then we rerun the model. You can see now that the model has been corrected so that it goes through that observation at that point. And so this improves the estimate of what our snowpack would be given an observation was assimilated. So let's take a look at how assimilation influences modeled SWE using a case study from our Wyoming modeling domain, which is where we did a lot of our initial testing. In order to perform this analysis, we first divided all of our SNOTEL stations in the domain in half. One half of the stations was used for assimilation, one half of the stations was used for evaluation, and all of the CSO observations that were submitted are indicated by those red pluses. We then conducted a series of numerical experiments. So we ran the model at the baseline mode with no data assimilation. We assimilated only CSO data, we assimilated only SNOTEL data, and then we assimilated a combination of CSO and SNOTEL data. And through these experiments, we found that the assimilation of CSO data is of equal or greater value than the assimilation of SNOTEL data. And this is demonstrated through 2 key findings. So the assimilation of CSO data improves modeled SWE compared to snow model runs with no assimilation, and the assimilation of CSO data in addition to SNOTEL data improves modeled SWE compared to the assimilation of SNOTEL data alone. So if we look at these 2 sites, which are evaluation sites, the red line shows you the observation, the dark blue line shows you that baseline snow model run, and then the light blue line shows you if we assimilate the combination of CSO and SNOTEL data. So you can see that that assimilation of data pushes the modeled result closer to the observations. This is super impressive if you think about it, considering that SNOTEL provides daily SWE observations that are regular in time, while CSO data is just completely submitted randomly by our users and is opportunistic in space and time. It still improves our modeled results, which is fantastic. And those experiments are what informed our data assimilation scheme for our operational product, which can be found at mountainsnow.org. We're really excited to launch this web application because it's something that we've had participants asking for since day one. So people want to know how much snow is out there in these really remote places, and so we want to give you really accurate estimates. And if any of you have already pulled out your phones and are looking at this, I just do want to warn you, this is optimized for desktop at this point, but hopefully that mobile optimization will be coming soon. Okay, so let's check out the app. This is the home page. So you can see each of our 13 modeling domains indicated by those little black boxes. I might have to use the... Okay, great. So if we zoom in, we are looking now at the Snoqualmie domain. We can select a date right here, and this will show you modeled estimates of whatever snow variable you've selected. You can also change your background map up here in this top corner. So this is showing satellite imagery in the background. I find it really useful to use this satellite imagery in the background if I'm looking at a specific ski zone. And through this app, you can view a combination of both satellite and modeled results. Let's take a look at the satellite products here. So we have the modeled CSO suite product that you're looking at here on the left. Then we have the Modus snow cover product on the right over the same domain, and then Sentinel satellite imagery on the right. And so you can go through the different domains on different dates and compare between these different products. You can also select any of these snow variables by clicking the checkboxes on the left, or you can open this pull-down menu to turn layers on and off and adjust the transparency. The default variable that you can see is the snow water equivalent, which is shown right here. The color bar that indicates what these colors mean is over here on the right side. And we have multiple other variables you can view. You can look at the snow depth. You can look at the 3-day change in snow depth to see where snow has been increasing or decreasing. And you can also take a look at how the snow depth is changed due to the assimilation of observations compared to the baseline snow model run. One thing that's also worth noting, right here, each of these snow variables has a slider on it, which allows you to adjust the maximum value, which corresponds to this color bar. So right now, the tops of the mountains are fairly washed out. So if I slide that over to 3, we can get better resolution and more visibility in our mountaintops. So early season, you need to make that lower. Late season, you make it higher. And you can also compare this to a nationally modeled product, which is called SNODAS. This is available on a daily timescale, but it's at a much coarser resolution than the CSO project. And none of this would have been possible without participation from an amazing network of snow professionals and recreationalists who are out there submitting snow observations. So thank you so much for helping both the science and all of us who are out there recreating. I'm happy to answer any questions, and if you scan any of these QR codes, this will allow you to download that the Snowscope app on your phone. Thanks. Oh, is that yours?
Thank you, Nina. Do we have any questions? Josh has got a question. Over there, but there's another question here. We'll take. we can get the question from the center and Josh afterwards.
All right, so I'm psyched to be a citizen scientist. What are the easiest ways to make my observation data invalid, and how do I avoid those when I'm physically doing my observation?
Yeah, that's a great question. You just want to find a place in the snowpack that's not very clearly disturbed. We have a lot of filtering to test, to do quality control on the observations that are submitted, but the most useful thing for us is finding an undisturbed place of snow. So you don't want to be in the middle of a sled track or a skin track. You want to just step off to the side and find a new patch of snow and sample from there. Yeah.
Have you done any point locations and verification of the model to see how accurate it is on the ground?
Yes, we have done a lot of that. One of the things that's worth noting, though, is we spun up a whole bunch of modeling domains. Some domains are tested more than other domains. So in Wyoming, we did a super thorough analysis, and the same is true of Alaska, where we have another domain that we've worked a lot on. We've done a rough analysis of all sorts of different assimilation scenarios across the other domains, and it does really well. To be completely honest, I was surprised that the CSO observations helped as much as they did, but it made a substantial difference, which was really exciting.
I was gonna ask what your favorite modeling program is, but you might have already answered that. Just a show of hands, I'm curious, how many people have taken part in the citizen snow observations here? Have any folks been doing it? A few?
Nice,
Awesome.
you got a couple of you.
Yeah, great to see that. Okay, it looks like we have another question over there.
Are the snow depth models prescriptive or to the future, or are they just historical?
So it depends on what forcing data you have. So if you want to run them into the future, we'd have to get forecast data that gives us meteorological variables going into the future. We have played with that. They're not on the app, though, that you can view right now.
Okay, great. Do we have another question, it looks like?
So how accurate do these models, these snowpack models, need to get for someone to be able to rely on it in an area where there's not a lot of other input like sensors? By someone, I mean maybe a forecaster.
That's a really good question. I think we'd want to do some closer testing in cooperation with forecasters so that we can tune the model for exactly what the needs are. One of the things that we've tuned for right now is water resources for downstream users and communities. So it changes depending on what your user is, on what you would really want to tune that model for.
And, well, looks like we have the person in the middle, and then we have a question from the online audience after that.
I was just curious if you thought about trying to pull NWAC public observations into your data set at all, because personally, it might be hard to remember to do both sets of observation every time I get out of the field.
Totally. This is a conversation that is ongoing, and I think there's a lot of hope that that can happen in the future. There's a lot of back-end pieces that have to come together to have that data pulled automatically, but it is hopefully something we're building towards.
Collaboration is exciting to have for that. And Robert, what
Yes, we have a question from the online feed. The question is, how are you calculating SWE from these citizen observations of depth without any citizen measurements of water content?
Yeah, that's a great question. We have an equation that we're using that takes in climatology and location that is used to convert depth to SWE for assimilation.
Great, thanks.
Yeah.
I was curious, Nina, do you take a look at the model most times before you get out into the backcountry, or how often do you take a look at it, or is that just for work or so?
I look at it all the time because I'm constantly comparing between products, I think is one of the things. And so I want to look at the SNOTEL station, I want to look at the model output, and often for catching those 3-day changes, I think is really interesting because sometimes it's not as intuitive seeing how that looks spatially, which is something that I really enjoy looking at on it.
Yeah, that overall map image is very impressive with it.
Yeah.
Going to be excited to take a look more at that this coming winter.
Yeah.
Great. And looks like we have one more question.
You have a chance to use LiDAR data for validation, specifically airborne LiDAR, which has super high resolution.
That's a great question. This past winter, we actually did do LiDAR flights in the Alaska modeling domain in the Chugach, and we are looking right now both at using that as a validation product, but potentially if we have infrequent LiDAR flights, using them as an assimilation product and comparing and weighing kind of what would be the strategy with that product. I'm really excited about that. working in Alaska was pretty amazing also. Not bad place to work.
Yeah, nice change of scenery. Okay, another question. We still have a little bit of time. Oh, there's a question towards the back in the middle.
Thank you very much for a great talk. Clarification on the apps and so you had the Snowscope app, which is up here. You have the, what was the desktop version only?
Oh yeah, okay, so you can submit observations on SnowPilot or Snowscope.
And was there also Mountain Hub? Was that a link somewhere, or is that?
So Mountain Hub was the app that we used previously, but we've replaced that with Snowscope going forward.
And is there any convergence back and forth? But can you export SnowPilot stuff into Snowscope, or can you change? Like, can you go back and forth for users who are already in one platform, moving to another?
I do not believe that you can interface between those two platforms, but all CSO observations are available in one combined location if you go to communitysnowobs.org.
But moving forward, if you want to keep records of the Snowscope is the best option for mobile records.
For mobile, yeah.
Okay.
Exactly.
Thank you.
Yeah, for submitting that basic, just snow height sort of information, then definitely be getting that Snowscope app to do a quick and easy observation submission. Fun thing to easily and quickly do this winter when you're out and about. Okay, great. Well, thank you very much, Nina. Our last presentation here is oftentimes one of the most eagerly awaited talks of the day. If you've been to NSA before, he will be a familiar face. Nick Bond is a principal research scientist with the Cooperative Institute for Climate, Ocean, and Ecosystem Studies at the University of Washington. He is the climatologist for the state of Washington and a self-proclaimed proud weather geek. So, I know we're all on the edge of our seats to find out. Nick, how much powder are we going to get this winter?
Well, you got to stick around a little bit. And, so, just, yeah. So before I get started here, the landscape gets prettier around here. More residents get to wearing long pants. But apologies, I couldn't bring myself to it today. Let's see. My presentation. Oh, I just click. Yeah. Okay. There we go. So is this the scene that we're going to be seeing this winter, right? Let's hope so. What I'm going to review is, it's kind of a tradition of sort, a brief review of last year's winter weather, a little bit about what's going on with ENSO, El Nino, La Nina, and that sort of thing. And we're kind of giving away a punchline. It's a triple header La Nina, looks like we're having. I'd like to talk a little bit about a special topic, and I don't recall whether it was last year or the year before, one or more people asked about atmospheric rivers, and so we're just going to look into that a little bit, and then, of course, what the forecasts are. Okay, so for the months of November through March, on the left is what the temperature anomalies look like in the Pacific Northwest, and on the right, the precipitation. It was overall a little bit on the warmer side, but especially at the higher elevations. You can see the Cascades sticking up there in the reds that, a degree or two Fahrenheit above normal. The lowlands, pretty near normal temperatures, again, for that November through March period. In terms of precipitation, one size doesn't fit all. Western Washington was on the wet side, but Oregon definitely got ripped off along with southern Idaho, and so it was dry overall. those kinds of average or maps, mean values for a season don't tell the whole story. And in particular, this is an example of a time series of at top the temperatures in this instance at Paradise Ranger Station, with each day a blue bar starting October 1st, start of the water year, through the end of the water year, September of this year. And that brown band in the middle is the normal range between the maximum and minimum temperatures. And so you can see each day what it was like. And then on the bottom is the precipitation, the green line, relative to, I think those are the wettest and driest years in the record. They're the brown and blue traces. And what's remarkable about that, of course, is the last few months, even at Paradise, how dry it has been, just flattened out. That's the accumulated precipitation. And another thing worth pointing out, getting back to the temperatures at the top, is just how wet and cool the spring was this year. And going back over 100 years, I forget whether it was, and depending what region you look at, I think it was something like either the second wettest and the fourth coolest, or vice versa, or something. It was cool and wet, definitely. A little bit about some of the events that went on. There were some major atmospheric rivers late in 2021. A little bit more about that in a couple of minutes. This is just a scene from January this year. Flooding in the lowlands there in early January 2022. And this was the scene more in the mountains. And I'm going to put Mark on the spot. We like to do that, right? All three major passes across Washington State were closed for multiple days. Has there really been a precedent for that in the past, that long of a closure? And testing his powers of recall, but okay. Fair enough. I thought it was a record. And I don't know just how long, but it was impacting commerce. And you can see, the testimony from this person that spoke out, there's no chicken at all. Jeez, So a little bit more about, again, how the weather played out last year, and just focusing here on December of last year through March of this year. The blue trace there is the snow depth at Stevens Pass, and those other two traces are the last 2 years previous. And there on December 1, there was basically nothing at Stevens at, 4,000 feet maybe and change. And it's not like that never happens, but still, that's a drag. But then, of course, let's go back. While the blue trace there doesn't look so impressive at the end of March, then because of that cool and wet weather in the spring, we got about 5 feet, 6 feet of snow in April into May at Stevens. And so that quite impressive. All right, but let's now direct our attention to what's going on right now in terms of the tropical Pacific, ocean temperatures, and so forth. Here's a picture from first week of October of the sea surface temperature anomalies across the tropical Pacific into the North Pacific. Direct your attention to the equatorial band there where it's cooler than normal. La Nina conditions are present. And, but in the North Pacific, those yellow and red colors are not good news for us in that warmer than normal sea surface temperatures, when they're really warm out there, like they were in the winter of 2014-15, that definitely predisposes us toward having warmer than normal temperatures. They're not as extreme now as they were that year, but still that's a drag. But back to the tropical Pacific, what the models are showing in the upper left there as a whole, and just the kind of official forecast, are La Nina conditions staying present into the new calendar year and then kind of wimping out. And more likely than not, neutral conditions kind of later into 2023. On the lower right is traces from a bunch of different models, kind of statistical ones and dynamical ones, and you have to kind of consider them as a group. Most of them are continuing cold in the tropical Pacific, and with but then with a return to more normal conditions sometime in the next 6-9 months or so. All right. A triple header La Nina, is there precedent for it? Yes. We've had 2 times that's happened in the last 50 years. Once in the early to mid 70s, with the last of those La Nina winters being the winter of 75-76. The trace, the snow depth, again using Stevens Pass as an example, is there that gold trace with blue being the normal for the time of year. And so for that third of the triple header La Nina, there was a greater snow depth than usual. But our more recent triple header La Nina from the winter of 98, 99 into 2000, 2001, that was a bad one. Bad winter, no biscuit for you. But yeah, that very dry. If you go in the record back 50 years or something, that was way down there. All right. A little bit more about the forecast here in a minute, but I do want to talk just a bit about atmospheric rivers. And how many of you have heard the term? I bet most everybody and their dog has, yeah, okay. Pet peeve. The air in the atmospheric rivers is getting here did not originate in the tropics. The structure itself, you can see it there, but these systems process air as they're going. And if we really were getting air from the tropics, it'd be a lot warmer than it is. It is still disgustingly warm when a really strong one comes in here, but just again, I'll settle down, I promise, but it's just a kind of pet peeve. What the plot at the lower right shows is just the contours there are water vapor contents and integrated over the depth of the atmosphere. And no, I'm sorry, the color fill is that, and the contours are the temperatures, and you can see a characteristic of these atmospheric rivers is a plume of warm, moist air coming in, and as it shows in the cartoon on the left, that when it hits the terrain and goes up, big time rains, warm rains. And even though we had definitely some very strong examples of atmospheric rivers kind of back-to-back that hit northwest Washington last winter. And what I'd like to direct your attention to is a NOAA model, and I'm not sure if Nina knows from it's the NOHRSC product. Is this SNODAS that they're using for, that NOAA uses in it? I think it is. And, arguably I should know what I'm talking about, but you know better. But anyway, from the NOAA model at the top, this shows the snow depth anomalies. When was that? Early in November. And we got off to a pretty good start here in the northern part of Washington State anyway. And then those atmospheric rivers went through, and at the bottom, those red colors show where and that's on December 5th, is what the snow depth anomalies were, and obviously they did a real number on the snowpack, except for at the very highest elevations, the coldest spots in the North Cascades. A little bit about how during the height of that weather event, how that played out. On the top here in the next couple of slides is the change in snow depth over 24 hours. On the bottom map there is the change in SWE over the last 24 hours. This happened to be right at the end of November. And what you can see when this one of these atmospheric rivers was doing its thing, that it really decreased the snow depth, especially on the west side of the Cascades. There was a little bit of holdout of cold air in the lee of the crest, and so the snow depth actually went up some there. This is on the 28th of November. Where from a sweep point of view, except for at the lowest elevations on the west side, you were building up the water content of that snowpack. You know, some of it was probably running through channels, but some was being soaked up kind of like a sponge or something. But then if you look at the next day, this is something that I think is pretty characteristic, and you avalanche forecasters, you tell me, you know, where I'm interpreting this wrong, but looking at the snow depth, everywhere it's going down, and at this point, it's just at the very highest elevations that you're kind of adding to the SWE, you're mostly decreasing it, because at a certain point, the snowpack isn't acting as a sponge, it's actually getting melted. And you know, what was left, you know, was certainly concrete, the Cascade concrete, right? All right. So we got a La Nina. Does that mean more, and it was La Nina last winter, more atmospheric rivers, less atmospheric rivers, you know? There it's kind of ambiguous. On the top chart there shows the number of winter days with atmospheric rivers, you know, relative to normal during El Nino. The bottom map is during La Nina. You can see for California, it'd be an easy answer to that question. Definitely more atmospheric rivers with El Nino versus La Nina. At least the, except for the very strongest ones, they're a good thing for their water supplies and snowpack and that sort of thing. They rely on those for a high percentage of their winter precipitation. For us, it's kind of a little bit mixed bag, and you might be surprised that we actually tend to get fewer of these atmospheric rivers just because the flow tends to come a little bit more from the northwest in La Nina than in El Nino, and it's that west-southwest or southwest flow that is the kind of atmospheric river sort of setup. All right. With global warming, we can look forward to more of these bad boys. Yeah, I guess that's a, you know, editorial comment or so. For what it's worth, in this paper, it's been divided up. The really strong ones, the kind of category 4s and 5s at the bottom, the kind of middle of the road ones in the middle, and the kind of weaker ones at the top, with again the really strongest ones in big floods and then do damage, but the other ones are probably more beneficial than detrimental. And where we see the increases are really here in the Pacific Northwest, and especially on the west side of the Cascade Crest. All right, so let's get into the forecast. Here, what I'm showing is, and there'll be a few plots like this, a map, or a series of maps. On the upper center is the 500 millibar anomaly forecast, in this case for December through February. On the lower left is the temperature at 850 millibars, about 5,000 feet, 4,500, 5,000 feet or something. Thought that was more meaningful than surface temperatures. Moreover, the models do better at those kind of free atmosphere sort of forecasts than what's happening at the surface where there's a lot of other things going on. And then at the lower right is the precipitation relative to normal. What the model, and this is from a group, the International Multi-Model Ensemble, including the results from models run both in the US, Canada, and mostly in Europe. And I think this has maybe a little bit better performance than the National Multi-Model Ensemble, but they're real comparable. The screaming message is that it is, they're suggesting that higher than normal heights aloft, that means higher pressure aloft. This is 500 millibars at 20,000 feet in the atmosphere. So over the North Pacific, negative anomalies over Canada. With that sort of configuration, more flow from the northwest than usual. And that's what we like to see for snow in the mountains, right? And the consequence is, while the flow is the right direction, those heights being higher than normal kind of shows that the atmosphere is not abnormally cool necessarily. And then remember, the North Pacific is kind of on the warm side too. And so our temperatures forecast by these models, this group, are near normal, but with that northwesterly flow, especially on the west side of the Cascades, greater than normal precipitation. And that may be kind of seemingly preposterous in recognition of the kind of weather we've been having the last few months, but this is what the models are showing. And getting back to, it's kind of just easier to look at a group of the models from the National Multi-Model Ensemble. And what I was struck by is when you're looking at the individual ones, and here the international ensemble is in the lower right there, is that they're all showing greater precipitation than normal for western Washington and the west slopes of the Rockies, northern Rockies. In terms of, when this is really going to kick in, the very latest series of runs from the US model is showing, October has been a disaster so far, and then it's going to turn around in about a week or so, but still, there's so much catching up to do. October is going to be on the dry and warm side, but by at least later into the winter, we'll be getting into more normal or even temperatures maybe a little bit on the cool side, and then on the wet side also. And just for fun, I went ahead and looked at the relationship between precipitation in Seattle in October on the horizontal axis, and for the climate zone, that's the western slope of the Cascade Mountains for the rest of winter, just November through February, and there's really no relationship there, so don't panic. Last year, this is what the forecast was. Does that look pretty familiar? That again. And it wasn't bad. When you actually look at the verification, it was a stronger representation of that pattern, but the idea of high to the west, lower than normal heights over Canada, that's what actually happened. So just in the last few seconds here, I know everybody wants to go to happy hour and go outside for a bite of fresh air or something, right? Think about it. It's beautiful this time of year when it turns from green to gold to brown, and I'm talking about the air, right? So anyway, okay. So the forecast here from the Climate Prediction Center. Again, temperature, not much of a signal in the upper left. Precipitation, a little bit on the wet side, early in the fall season here, overlapping it a little bit into December through February. They're basically going with the canonical La Nina signal of it being cold in the northern part of the Pacific Northwest. Not so sure about that, but I'm okay with it being a little bit on the wet side anyway, and continuing perhaps into spring. And so just to close here, sure, we've gotten a terrible start to the season, but don't give up. And, you know, La Nina is basically more or less guaranteed, at least for a few more months. And it's not always, but it does stack the deck for us to have wet and cool weather, and at least a decent snowpack. The spring of 2021 was really dry. This last one was really wet. We can't really forecast that very well. And so I'm hoping there's no questions about what it's going to be like in spring. So I'm just going to say that. And I'll just leave this up here, and then, you know, I want to hear from you. Thanks. Come on, don't be bashful.
Thank you, Nick. That was great catch up for the season. I sensed all the certainty. Oh, we've got a question from Mark. I was
How come I'm
having
not surprised?
more El Nino poems running through my head.
Yeah, or haikus. A haiku.
Haiku.
Can we
How
get a
are you?
reciting?
I have a question about a forecast for the short term.
Okay.
Will you be skiing in your scarecrow suit by Halloween?
Yeah, that's right. No, the short-term forecast is actually really promising. And again, it may seem like, what are you talking about? But, you know, remember you heard it here first or something like that. And that actually it's a pattern that if it was a month or two later into the year is pretty similar to getting really low elevation snow in the Pacific Northwest. That's not going to happen, but certainly the freezing levels are going to come down to, you know, 5,000 feet or so, and it looks like some precipitation. And again, I encourage any of my, you know, forecaster buddies to weigh in.
I sense certainty of change coming up.
Yeah.
Yes. Okay.
People are thirsty, right?
Do we have more questions for Nick?
Yeah.
Oh, we've got one in the back corner over there.
Oh, good. I'm paid on a commission basis, and so I was promised 10% of the door too.
So there we go.
Yeah.
So my question's not actually about the forecast. It's about one of those atmospheric rivers last year. The one, I think it was November, that produced that record flooding for Bellingham, the Fraser River Valley, the Coquihalla Highway was shut down.
Right.
We were just, you know, as the snow community, it wasn't snowing, so we didn't care as much. But it was huge. It was a huge event. And we weren't in forecast operations, but my sense was that it was under forecasted on both sides of the border. And I'm curious historically if you've got, it just did so much damage. I think our Baker station had 15 inches of water or something.
Yeah.
Like, can you just put that in perspective for us?
Yeah, well, I think the forecasts were actually pretty good there. One of the things that happened was a levee failed in Everson, I think it is, and some of the Sumas River, that's what really did the damage into Sumas and Abbotsford, in that there was a kind of a failure of the infrastructure. And it turns out they just put up some flood walls in Mount Vernon, and that came out looking pretty good in that event. And so my recollection is, at least in general, it was anticipated. You know, we do a pretty good job of identifying the events. We don't always get the magnitude just right and exactly where it's going to play out and so forth. But it was, it's not like in the old days when we were caught completely by surprise and like, where'd that come from? Well, we knew that it was going to be some problems. Go. I bet you can shout. Yeah. Oh, well, maybe not.
Thank you. Yeah, just I wonder if you could give us kind of longer-term prognosis in the context of global warming, what we should expect for snowpack and implications for Pacific Northwest.
Oh, well, yeah, that's kind of a grim note there. You know, basically what we're seeing is already declines in snowpack, especially by the end of the winter season, and it. You know, the trends are down there. There's plenty of year-to-year variability, and I'm glad you actually brought that up because there's some real recent research that has shown that unlike what the climate models are showing, in the actual observations, there's been a higher proportion of La Nina events compared to El Nino events than there were in the historical past, and the benefits we get from La Nina. And so there may be some mitigation of that sort. And the models in the kind of decadal scale predictions are showing more El Ninos in the future, but they may be getting some of the physics wrong with the effects of fresh water on ocean circulation and, you know, all sorts of stuff. And so but that being said, in most places where we've got long records, the snowpack is systematically going down. And with warmer temperatures, it's hard to believe, albeit wetter winters, except for the higher elevations, that's going to continue to be the way it goes. It is, the one good news is that the Canadian Rockies, the upper parts of the watershed of the Columbia, are still going to be cold and snowy for the foreseeable future. And so it's not like we're going to necessarily run out of water. It's just we're going to have it, more of it when we don't need it and less of it in the summer when we really need it. But that's a whole another can of worms. Anybody else? Oh, getting there. Okay.
One more question about the wintertime surface pressure east of the Cascades. Have there been any long-term or even in short-term studies about the average surface pressure east of the Cascades to help the easterly flow situation to keep snow in the passes?
Yeah, a great question there about the, that critical east-west pressure difference that, drives cold air at low elevations through, especially Snoqualmie, Stevens Pass, and so forth, and can kind of keep cool air where we, in those locations. And that came up before. I looked into it, and I struggled to find some kind of definitive results there. And so it sounds like you're telling me that next year I should come equipped with something about that. Is that what you're trying to say? I'll be back. Yeah. In general, I'd be kind of pessimistic about that. And some of the modeling results are showing places like Mount Baker are going to hang on to their snow longer than places like the Snoqualmie, Stevens Pass, and so forth, because that supply of cold air requires cold temperatures in the low elevations east of the Cascades, and as we put more crap into the atmosphere, greenhouse gases, that supply of cold air is liable to shrink. And so it's, and with that cold and dense air is higher pressure. And so my guess is that in the long term, there will be a decrease in that east-west pressure gradient, but it may be tricky to tease that out from the observations so far. And that's what I got to plead ignorance on. Oh, got another customer?
Yeah. Coming back to your comment about more moisture when we really don't need it and less moisture when we do need it in the summer. Can you comment about fire season next year?
Yeah, and in the last 20, 30 years, we've definitely seen drier summers in the Pacific Northwest, whether it's just a dress rehearsal or is it really climate change already being manifested. But the climate models as a group are showing drier summers and wetter winters. We're not seeing those trends in the observations in the winters yet, but at least again back to the 90s or so, we are seeing the drier summers and the consequences, you know, like I said, help yourself to a bite of fresh air, right? Oh, hey, yeah, Robert.
This is a personal rather than online question. I'm wondering if you've looked at the polar vortex shedding events and sort of any trends and how they affect us here in the Pacific Northwest.
Yeah, I have not. And so what he's talking about is certainly in the area of active research in the climate community and controversy just about what's happening in the Arctic, how that is affecting the polar vortex. And it probably has much more to do with the kind of the weather in East Asia and Eastern North America. But that being said, certainly for our cold air outbreaks, it plays a role. And so, yeah. That's my non-answer.
Lowland snow events.
Yeah, and so, you know, we could vote. Do you want to know more about, you know, east-west pressure differences or polar vortices for next year? And so, anyway, I'll decide no matter what you guys vote on.
Okay.
Yeah, all right.
Thank
I think it's game over.
Yeah.
Thanks.
Thank you very much, Nick. It's always wonderful to hear you boiling down the summary for our upcoming winter into that short period of time.
And I like giving good news. So when it's El Nino next year, get somebody else.
Okay. We'll have somebody else come in for next year. Excellent. So this concludes our speakers for today. However, in case you are not sick of seeing me up here on the stage yet, at this point, we have the film, The Bottom Line, which Dennis spoke about at the beginning of the day. And so we are going to be showing that now. And so basically, last year, we all, myself and Lee and Matt at one point got together with the film team and got out into the snow and wanted to share with you all, both in the snow and in the office as well, a bit of an insight into the life of a forecaster. And so I hope you all enjoy this. Let's get it started. Oh, not quite done yet. Still got a few more slides on the weather. More questions? Okay.
All backcountry travelers, anybody, no matter what people are doing, they each shoulder the responsibility for their own risk. The pressure as a forecaster is if I give them the wrong information. If I don't address the right avalanche problem and they go out expecting one thing, and then in reality, there's a different problem. Or you say the avalanche danger is going to be one rating and it ends up being more hazardous than that. Now, in the avalanche education world, you start with the avalanche forecast, but then you make your own observations after that to look for what the forecast is talking about. But if you see something that doesn't line up and indicates more danger, you take the responsibility on yourself to change your plan.
My name is Irene Henninger.
And I'm Lee Lazara, and we're both avalanche forecasters with the Northwest Avalanche Center, and we forecast for the West North and West Central zones.
I ski patrolled between Montana and New Zealand for 23 winters, and so while I was doing that, I was also teaching avalanche courses. But then I looked around for some forecasting jobs, and I ended up taking the job at the Northwest Avalanche Center.
So the path to me becoming an avalanche forecaster was just by being a skier, by being someone who loved skiing, loved being in the mountains, and was particularly attracted to being in avalanche terrain as a backcountry skier. I lived in Little Cottonwood Canyon, and I ended up staying there long enough that I landed on the Snowbird Ski Patrol. I worked as a guide for a handful of years, as a ski guide, a mountain guide in the Northwest, and I started working with the Northwest Avalanche Center as a pro observer and did that for 5 years. This job as a forecaster came up in the last year, and I applied, and happy to be part of the organization since 2015.
NWAC is a public-private partnership. The U.S. Forest Service provides avalanche and weather forecasting, and the nonprofit NWAC provides outreach, education, and fundraising.
Our goal at NWAC is to consistently provide an avalanche forecast that's expert, professional, and clear, that is something reliable for people to use so they can understand each day how much danger they can encounter from avalanches when they're in the mountains, but also where they can go to do what they're out there to do to begin with.
What's really important to me is that I don't want to make this all sound negative, just like don't go here, don't go here, don't go here sort of thing. I mean, really, a lot of the times, that 25-degree powder slope would be nice to get on. Or if you're a snowshoer, maybe just rerouting your plan to travel on a different trail.
My day as an avalanche forecaster actually begins the evening before. It's finding partners, talking with my partners, figuring out where we're going to go, why we're going to go there, why is it a good idea, or why shouldn't we go to this place and maybe go someplace else. Looking at the forecast that comes out at 6 p.m., looking at weather forecasts in addition to the avalanche forecast.
The morning that I want to get out, I check the avalanche forecast again. I also look at the weather again, and I also maybe see if there's any updated observations which might change my plans based on whether somebody potentially headed out and encountered conditions which might be different from what I expect to see out there.
When our day in the field finishes, in a way, that's when the workday really begins. That's where we go from the being out in the mountains and looking at snow and getting a little skiing and getting some exercise to sitting down behind the computer with a lot of raw information and trying to take that information and then put that together with a weather forecast to actually produce the avalanche forecast for the next day. Forecaster meeting ends hopefully at 3:30, and that's basically go time. We have 2 hours and a little bit more to take the ideas that we were able to consolidate during the meeting and actually put those ideas and the danger rating and the problems into the thing that people read when they look at the avalanche forecast.
With red flags more than any of these other basic information pieces that you gather from the avalanche forecast, just looking over avalanche incidents, so many of the times when people are caught in avalanches, it's because they ignored an obvious red flag. The main red flags are recent avalanches, recent snowfall or wind loading, cracking or woomping, and rapid warming. With everyone becoming more aware of that and really trying to pay attention to whether a red flag occurred and immediately reevaluate what I'm doing and where I should be traveling, that's one of the most important things that I could be doing in order to avoid getting involved in an avalanche.
I didn't realize until I started working as an avalanche forecaster the level to which creating an avalanche forecast is a community effort. So myself or Irene or the other forecasters and observers at NWAC, even if we went into the mountains every day and were able to see terrain and go to all these places, we would never be able to gather all the information that we needed to create the product we do. It is dependent on other people providing us information, and then we're going out just to get our own understanding of what they're able to provide us.
For starters, submitting observations is something that is so incredibly helpful to us. Becoming a member, and then also taking avalanche courses as well is something that's incredibly valuable for yourself and to help become a more helpful member of the community.
when it's raining and it's windy and the skiing is horrible, we still go into the mountains. That's our job, to go out there when no one else is out there. So we go skiing so you don't have to. Those really terrible days, I have to pay just as much attention to those as I do to the days that are awesome when people are skiing PAL and there's a lot of people out there.
My goal as an avalanche forecaster is to be able to provide you with as much information as I can so that you can have a fun day in the backcountry and get home safely at the end of the day.
All right, well, that was great. Thanks, Irene. Thanks, everyone. Before we adjourn real quick, if you participated in our raffle, these are the raffle winners, and we'll request that you bring your ticket down to the NWAC raffle booth at the front of the building. But before we adjourn, I just want to give a round of thanks to all of the NWAC staff and forecast team who put this event together, all of the volunteers who helped make it happen, and then, of course, all the speakers who showed up to help share information and present for us. And a real quick logistics note, if you were a speaker, we'd love you to meet us downstairs in the green room prior to the community happy hour. And so we'd also like to invite you now downstairs to come grab a drink with us. We have some beers and we also have some non-alcoholic drinks for you. Please check this raffle ticket, and then we'll have I think there's a QR code slide, I believe, correct? Oh, there's not. I'm getting the message, no QR code. We'd love to know how today went for you all with a survey. There's a survey that'll land in your inbox here very shortly. So please fill out, tell us what you think. We use that information to help improve this event for next year. So thanks everyone for attending and for being a member of this community. And we'll see you downstairs. Thanks.
You gonna